Okay, so I think the time is. So the first speaker of this afternoon session will be Haidong Yuan from the Chinese University of Hong Kong, and he will tell us about precision limit of quantum metrology. Please.
Right. Thanks for the introduction. So I'm going to talk about this precision limit in quantum metrology. So in the morning, Professor Masahito Hayashi already gave a very good talk on this quantum metrologies, but still I'm going to first give some brief introductions just to fix the notations. And then I go to talk about how to get the highest precision limit for single parameter quantum estimations. Then talk about the multiple parameter case. Right. So as we have heard in the mornings, so the quantum metrology is basically is about estimating some unknown parameters. So here we're considering the unknown parameters is encoded in these quantum channels, right? So this CPTP maps in general, and it encodes some unknown parameter we denote as X. Right? To estimating these parameters, we need to go through a few steps. So first, we need to prepare some initial probable states. So this you can using some ancillary systems to help you, and then get the final states. After you're getting the final states, which is now encoded the unknown parameters, you can pick a set of POVMs to get the measurement results. And this measurement result will have certain probability distributions given by the Bound's rule. And from this measurement results, you can constructing and estimating functions we call X hat. Right? So in general, here we only considering this unbiased estimators, which is equal to true value at this true point. But we only considering this unbiased holding only near the true values in a small neighborhood of the true values. So this is locally unbiased. Now the goal is to minimizing the variance of these estimators. So the smaller the variance just means that it's like the red curves, you have a more like a narrow distributions. So with this, you have a small errors for your estimators. If you have larger variance, it's like distributed along like the blue curves, then there's higher probabilities your estimators will be far away from the true values. So our goal is trying to make the variance as small as possible. So this corresponding to a higher precisions. Right? So we have heard from the last lectures. So this variance can be quantified by a quantity called the Fisher informations. So these classical Fisher informations can be calculated from the probability distributions of your measurement results. So this is the formula to calculating the classical Fisher informations. And if you optimize your measurement to maximizing the classical Fisher informations, you will get a quantity called the quantum Fisher informations. So there's a bound, famous bound called the Cramer bound, says that now at least for the single parameter case, the lowest variance you can achieve is given by this inverse of quantum Fisher informations. Often here, the mu is the number of measurements you repeated. So this bound holds when the mu is sufficiently large. So this is a quantum Cramer bound, right? So you can, if you haven't seen this Fisher information or quantum Fisher information previously, you can intuitively understand this Fisher information just quantifies the distance between neighboring probability distributions or neighboring quantum states. So this is the process we just described. Now you can just imagine that if the X is deviated a little bit, shift a little bit to X plus dx, then the final state will also shift a little bit. Under the measurement, your probability distribution of your measurement results will also shift a little bit. So the classical Fisher information just describes how fast this probability distribution shift with respect to dx, right? And if you optimize the measurement, then the quantum Fisher information just describes this distance between neighboring quantum states, or for how fast this final states shift with dx. And if you can further optimize your probable states, then sometimes we call it like a channel fishing machines. The channel fishing machine will corresponding to the distance between neighboring content channels, or how fast these channels shift with dx. Right? So this relationship between the distance and the fishing machine can be quantified by certain distance functions. So for example, the classical fishing machine is related to just the Euclid distance of the square root of the probability distributions, right? So this distance is proportional to the classical fishing machines. And if you optimize the measurement, then this distance becomes the distance between quantum states. Basically, this is just the Bruce distance. This will be proportional to the quantum fishing machines. And if you further optimize the probable states, then basically the maximum quantum fishing machine you get will be proportional to the distance between the neighboring quantum channels. Right? So this classical distance or the Bruce distance, we have seen like a lot. It's widely known, but the distance between quantum channels are not that well known. So I'm going to first talk about how to calculate the distance between the quantum channels. Right? So for unit channels, the angles between the two unit channels, or the distance between two unit channels, have been obtained previously. So we can quantify the distance between the two unit channels as the maximum angle between the two final states when you optimize the initial states. It turns out that for unit channels, we do not need ancillary systems to achieve the maximum angles, right? So in other words, using ancillary systems does not help you to maximizing the angles. Just using the system will be sufficient. Right? And this cosine theta will be corresponding to the fidelity between the two states. Right? So to get the maximum angle, or to get the angle between these two unit channels, this problem actually has been solved previously. So it turns out that if you're calculating the eigenvalues of U1 DAG U2s, these eigenvalues will be complex number distributed around unit circles. And you just look at the minimum arc contains all the eigenvalues. And this angle will corresponding to the angle between the two unit channels. Right? This can be generalized to noise channels. So if we have two noise channels, you're using Stein dilations to like encode it as a part of the unit channels on the system and the environment. Then the angle between two noise channels is just the minimum angle among all possible unit dilations. And this, if you take the cosine of these angles, this will corresponding to the minimum fidelity between the output states assisted with ancillaries. So for noise channels, typically the ancillaries can help you to maximizing the angles. Right? So in this, for the noise case, the ancillary system is necessary to achieve the maximum angles. Right? But this is just kind of a correspondence, or you can see as the definitions of the angles. It does not tell you how to calculate. So it turns out that you can calculate these angles using the cross operators of the two noisy channels. So this maximum angle just corresponding to some minimum eigenvalues of some operators. And these operators can be obtained by combining the cross operators from the two noisy channels. So there's still a degree of freedom, which causes W here. This degree of freedom comes from the equivalent representations of the cross operators. But you can calculate this maximum over this degree of freedom using the semi-definite programmings. So this can be calculated efficiently. Right? So using this, you can obtain the maximum quantum fishing machine when you optimize the initial probable states. And you can also using the dual programs to get the optimal probable states. Right? So this kind of give you a hierarchy of the phishing machines and the distance between probability distributions and quantum states and the quantum channels. Right? So let's look at just the simple examples. For example, suppose we have phase estimations, but with damping channel, amplitude damping channels. And then you can using this mechanism we just talked about to calculating. First, you can write down as in terms of cross operators. Then you can using the cross operators to calculating the maximum quantum information you can obtain by optimizing the probable states. So in this case, just substitute into the semi-definite programming, or actually in this case, this semi-definite programming can be solved analytically. You can get analytical formula of the maximum quantum information. You can also get analytical formula of the optimal initial states. So this is for optimal probable state with a single use of the quantum channels. Now, if you can use the channels multiple times, then you also have another degree of freedom to optimize. So you have kind of what you call optimal strategies. So in this case, then the highest precision you can get will be proportional to the distance between the quantum comb or quantum process matrix. So what do we mean by optimize the strategies? So there are different strategies you can consider to arrange multiple channels. So widely used is the sequential strategies. They just put the channel sequentially, but in the middle you can add in some controls. Another one widely used is the parallel strategies. So the channels acting on each particles parallelly. So both sequential and the parallels you are allowed to using ancillary systems. And then besides this widely used parallel and sequential strategies, so recently there's also some interest in using the quantum switch, which was first proposed by Guilio Chilipara and the collaborators. So essentially the quantum switch is just using an additional control systems. So for example, simplex case is just using a qubit as the controls. So if the qubit is in zeros, you can go for example, first go through Alice and Bob. If the qubit is in one, then you first go through Bob and then Alice. And you can put the controls in superposition of 0 and 1. So then you are in the superposition of the two different passes. Right? So this is the simplest quantum switch. You can apply this using the quantum charges. So you can put these two channels in the quantum switch controlled by qubits. Right? You can generalize these quantum switch strategies to allow additional controls in the middles. So this gives you a generalized quantum switch. Right? So in the most general case is that we allow a general indefinite causal order strategies. So in this case, we only restrict the input and output are just the quantum states. But the process, we don't put much constraint in the process matrix. Right? But in the most general case, it is not known whether it can be realized physically as using any quantum circuit. But the quantum switch and the generalized quantum switch, it can be realized physically. Right? But for any strategy that you choose, so we can using semi-definite programming to calculating the maximum quantum information you can get by optimizing the strategies, probable states, and measurement. Right? So this program you can find out in these papers. We are not going to describe in details, but just for any system quantum channels, you can first decide which strategies you want to use. For example, parallel, sequential, or quantum switch. Then you can plug in the programs, and this program will give out the corresponding maximum quantum information you can obtain. Okay. Again, for example, suppose we're considering this phase estimations with the amplitude damping channels again. And if we're just considering using the channels twice, right? Then to calculating using the semi-definite programming, we can obtain the corresponding highest quantum information on the different strategies. So we plot these curves are plots of parallel strategies, sequential strategies, quantum switch, and this generalized quantum switch, and also the most general case with indefinite causal orders. Right? So the most general case with indefinite causal orders give the highest values, but it's not known whether it can be achieved in all cases. Right? But there are some regions, this superpositions of even the quantum switch is already equal to the highest values. So it means that in this case, the quantum switch or the generalized quantum switch is optimal among all possible strategies. Right? Or you can also see that in certain regions, this quantum switch is better than the optimal sequential strategies and the parallel strategies. So this semi-temporal programming not only give you the highest phishing machines, you can also using it to reversely engineering to give you the optimal circuit. So for example, this reverse engineering from the is also kind of developed in these papers. Right? So we just applying it to our case. So for example, in the optimal sequential case, once you're applying our semi-temporal planning, gets optimal strategies, you can reverse engineering it to get the optimal circuits. So in this case, for these two noisy channels, the optimal circuit is given by these two controls. You will start from 0, 0, 0, 0s. So you need 4 qubits to achieve the maximum quantum phishing machines for 2 use of the noisy channels. And the 2 unitaries are given by the circuit here. Right? It's a bit complicated, but it gives you a benchmark of the highest precision you can get. Right? So this is for the single parameter case. So essentially for the single parameter case, we have a relatively good understanding about how to optimize the probable states and optimize the measurement, optimize the strategies to get the highest precisions. Right? But for the multi-parameter case, the situation is much more complicated. So for multi-parameter estimations, where now X is not just a scalar, but the vectors. So there's a multiple steps that you may have some kind of incompatibilities. So by incompatibility, we just mean that the optimal strategy for estimating different parameters may not be compatible, right? So for example, in the measurement stage, so the optimal measurement for the estimation of different parameters can correspond to different POVMs. And different POVM may not be compatible, right? So when you're choosing the measurement, then you have to make a trade-off among the precision limits of the different parameters, right? So similarly, incompatibility happens when you're choosing a probable states. So the optimal probable states for estimating different parameters may be different, right? So when you're choosing a probable states, you have to make trade-offs among the precision limits for estimating different parameters. Right? This incompatibility can also happen when you have multiple channels and you are considering the optimal strategies. Right? So the optimal strategy, for example, in the sequential strategies, the controls you added in the middle may be different for estimating different parameters. So you also need to make trade-offs, for the estimation of different parameters. All right. So there are various incompatibility will arise in the multi-parameter case. So which makes the multi-parameter quantum estimations much more complicated than the single parameter case. Right. Right. In this talk, we are going to mainly focus one aspect of this incompatibility, which arises from the measurement incompatibilities. So we assumed you have picked probable states and picked strategies, and you have get the final states. Now let's look at what are the incompatibilities caused by the measurement. Right? So for this, we had to again review what we have known as to quantify the precision limit when you have given the final states. So for given the final states, we know that the Clammer bounds give you a achievable lower bounds on the covariance matrix in the multi-parameter case, right? So you just after you choosing measurement, you have a classical Clammer bound, and this classical Clammer bound will be further bounded by the quantum Clammer bound, right? And this quantum Clammer bound is, as we have talked about, is proportional to the Bruce distance, right? Right. So the different from the single parameter case is that now for the multiple parameter case, the quantum Fission matching becomes a quantum Fission matching matrix, and the classical Fission matching also becomes a classical Fission matching matrix. So we are not just having a number, but having a matrix, right? And this matrix can be calculated from the quantum Fission matching matrix can be calculated from the quantum states. This is standard formulas to calculate the quantum Fission matching matrix entries. And the important thing here is this SLDs. So this LJ, the SLDs, symmetric logarithm derivative corresponding to the parameter xj, which can be obtained from these differential equations. Right? And the classical Fission matching can be obtained from the probability distributions of the final measurement. Right? Now, in the single parameter case, we can always choosing a measurement to make the classical Fission matching equal to the quantum Fission matching matrix or Fission matching. But for multiple parameter case, this may not be the case. So we can think about measurement as a special of quantum channels. These measurements you can think about it as quantum classical channels, but it is still a quantum channels. So from the data process inequalities, so the states going through the measurement, the distance will all cannot increase. Right? It will be equal, at most equal, or decrease. So from this simple data process inequality intuitions, we can immediately know that the classical Fission matching matrix always is smaller than quantum Fission matching matrix. Here, small in the positive, semi-positive definite sense. So FQ minus FC is semi-positive definite. Okay. So we already know that for in the single parameter case, there always exists a measurement that makes classical Fission matching equal to the quantum Fission matching. And the one choice of the measurement is just taking the SLDs as the optimal observables. So perform the project measurement on the eigenvectors of the SLDs, right? So the SLD serves as an optimal observable in the single parameter case, right? Now in the multiple parameter case, so the different SLDs correspond to the different parameters may not be compatible, right? So in this case, so in general, so there may not exist a measurement that can make the quantum classical Fission matching matrix equal to the quantum Fission matching matrix. If this happens, then we say the measurement for different parameters are incompatible, right? So this just means that the quantum Clammer bound is in general not settable for a multi-parameter case. Right? But what is the lowest covariance matrix you can achieve in multi-parameter quantum estimations? So this will depend on the set of measurement are allowed, right? So in general, we are going to classify the measurement according to the collectiveness, right? So if you can only perform separable measurement on each copy of the quantum states, then we call it like a one local measurement. And if we can perform collective measurement on 2 copies of quantum states, we call it a 2 local measurement. And if we can first prepare P copy of the states and perform collective measurement on P copies of quantum states, then we call it a P local measurement, right? So the 1 local measurement is the most restricted, and the 2 local measurement and including 1 local as special cases. So the larger the P is, the larger the set of the measurement, right? So you will get, if you optimize over all these measurements, then you will get a lower covariance matrix if P is larger, right? So we are going to kind of, here we're just studying what are the maximum classical efficiency matrix you can obtain under different P local measurement, right? So we are going to quantify this gap or a similarity between the classical efficiency matrix and the quantum efficiency matrix using a quantity as this big gamma P, right? So because the classical efficiency matrix and the quantum efficiency matrix are just a matrix, so we need a scalars. So we construct, you can construct a scalar using these quantities. Basically, this quantity quantifies how close this classical efficiency matrix is to the quantum efficiency matrix, right? If the classical efficiency matrix can achieve the quantum efficiency matrix, then this gamma P achieves the maximum value, which is n. Here n is the number of parameters, right? And we know that this quantum efficiency matrix is additive. So if we have P copies, if we are allowed to perform P local measurement on P copy of quantum states, the quantum efficiency matrix on P copy of quantum states is just P times of a single copy of quantum efficiency matrix, right? But the classical case, the classical efficiency matrix, in general, is not additive. It's in general, it's super additive, right? And you can intuitively understand that this gamma P, if you substitute FQP equal to P copy of a single quantum efficiency into the formulas, you can intuitively understand that it's just evaluating on average on single copy of quantum states, which is average classical efficiency matrix, how close this average is to the quantum efficiency matrix, right? Because the classical efficiency matrix is always smaller than quantum efficiency matrix, so there's a natural upper bound, a trivial upper bound, which is n, right? But we want to find out some non-trivial upper bound, which is in general smaller than n. So this is not the only quantity can quantify the closeness between classical efficiency matrix and the quantum efficiency matrix. So there's some works using kind of a inverse of the previous quantities. So previously we're using the FQ inverse marked by FC, right? But some works also using FQ marked by FC inverse. So this can also used to quantify the closeness between the classical efficiency matrix and quantum efficiency matrix. But in general, we need to find the lower bound. So there's a trivial lower bound, which is n. So this is always bigger or equal than n. So you need to find out the larger lower bounds if you're using these quantities, right? But if you're using the Cauchy-Schwarz inequalities, the 2 measures of this can be connected by these Cauchy-Schwarz inequalities, right? So the upper bound on these quantities can be immediately converted into the lower bound on these quantities. But conversely, it's not true. So if you just find a lower bound on these quantities, you cannot using this Cauchy-Schwarz inequality to convert to the upper bounds of these quantities, right? Because you have the bigger or equal than. So this cannot give you an upper bound on these quantities, right? So for these reasons, we're going to using the upper bounds on these quantities as a measure of the closeness between FC and FQs, right? Because it can be converted to lower bound with other quantities. Right. So let's first review a little bit what we have known previously. So we have already heard from in the morning in Hayashi's talk with different bounds that is already known, right? So if you allow infinite copies or correcting measurement on infinite copies, then the precision limit is given by this Harevo-Nagoya bound, right? I'm not going into the details of these bounds, which has been introduced in the morning. Right? If we only allow separate one local measurement, then for the two-parameter case, Nagoya has provided a tight bound and the Harevo-Nagoya bound. And this Nagoya bound has been recently generalized to n parameters as the Nagoya-Hayashi bound. Right? In the morning, we have also heard about the tight bounds can be obtained by conical programs. Okay? But these bounds are all need and sort of numerical optimizations. So there's also analytical bounds obtained by Gill and Massa. So this on the one local measurement, this quantity will be upbounded by d minus 1, where d is the dimension of the Hilbert space. So since we have a trivial bound like a gamma 1 should be upbounded by n, so this Gill-Massa bound is only non-trivial when this n is bigger than d minus 1. Right? So in 2021, Xiaoming Lu and Xiaoguang Wang has also obtained another analytical bounds using Ozawa's measurement uncertain relations. So this also most works for pairs of parameters. So this bound is tight for pure states with two parameters. For correct measurement on two copies of quantum state, Zhu Quanjun at Fudan University and Hayashi also obtained an analytical bound. So this gamma 2 will be upbounded by these quantities. Here D is again the Hilbert space for a single law. Right? The bound is non-trivial when you have parameters larger than this bounds. Right? We also know under which conditions this classical efficient matching matrix can achieve the quantum efficient matching matrix when you allow correct measurement on infinite copies of quantum states. So this is called the weak commutative conditions. Right? And if you only allow one local measurement, so there's a necessary condition for the classical efficient matching equal to the quantum efficient matching matrix, which is called the partial commutative conditions, which is given by these equations. So the partial commutative condition is stronger than the weak commutative conditions. Now let's give the analytical bounds for the multiple penny case. So let's first talk about the pure state case. So for pure state case, you can first calculating these geometric tensors with F. So this geometric tensor will contain the real part as the quantum efficient matching matrix, and also the imaginary part, which is kind of proportional to the Berry curvatures. From this, you can get an upper bound on this the quantity gammas. So for pure states, the one local measurement actually turns out is already optimal. So the correct measurement does not help you. So all these gammas collapse to be the same. And this gamma will be upbounded by these quantities. So here the F is the Fluid norm. Right? So this is a small, always if the second quantity is non-zero, this is always smaller than n. So which give you a non-trivial bound for any n. Right? And for mixed states, so correct measurement typically helps you. So different gammas will have strict hierarchies. Usually gamma 1 will be smaller than gamma 2, will be smaller than gamma infinities. And for each gamma p, you can get an upper bound. So as long as this quantity is non-zeros, then this will give you a non-trivial bound. From this bound, you can immediately obtain necessary conditions to saturate the quantum caliber bound, or necessary condition to make the classical fishing matrix equal to the quantum fishing matrix, which is this quantity Cp over P had to be had to be zeros, right? And this, when P equal to 1, this is just equivalent to the partial commutative conditions, right? And when P equal to infinities, this quantity, you can show that this quantity will converge to the weak commutative conditions. So this convergence, you can also proved using a technique in this. I was taught this paper contains some techniques can also prove this convergence. This is in Japanese, so I cannot point down in really precisely point down. So this upbound requires you using the operators on p copy of the quantum states. So this may not computationally may be hard, but you can also simplify the bound a little bit. You're just using the operators on single copy of quantum states. So this is, so instead of a CP, we're replacing with TPs. So I'm not going to not going into the details of the TPs, but just mention that the TP can be computed with quantities associated with single quantum states, not the P copy of the quantum states. So this will be less tight than TP will be less tight than the CPs, but the difference is proportional to the 1 over square root of P. So if P is large, then the difference is not that large. So these bounds, this gamma, bounds on gammas can be transformed into the bounds on the covariance matrix using the Cauchy-Schwarz inequalities. So for example, if we have a gamma P, the upper bound on the gamma P's, you can, using Cauchy-Schwarz inequalities, you can transform into this lower bound on the covariance matrix. Right. I think we are almost on time. So basically, we talk about how to get the highest precisions for the single parameter case, about how to optimize the probable states measurement and the strategies, which are corresponding to the distance of the classical probabilities, quantum states, quantum channels, and the quantum combs. Then we talk about some analytical bounds on the measurement incomparabilities. Basically, this bound quantifies how close your classical fishing matrix can be to the quantum fishing matrix. Right? Of course, there are many open problems in the multiple parameter case. So we haven't talked about the probable incompatibility and the control compatibility. Right? It is much less explored territory. There's many open problems. Right? So in the end, I want to make an advisement on positions, research assistant professor positions in my department. So if you are interested, please send a CV to this email address. Right. Right. Thank you.
Okay. Thank you very much for your presentation. So let's start from maybe people here in the physical audience, if there are questions.
Sorry, I have one comment. So I want to confirm one thing. So your talk composed of two parts. First part considering the one parameter case, and the second part consider multiple parameter case. But I think in the first case, you consider channel estimation problem with one parameter. channel estimation. And second setting, you only consider state estimation. You never consider channel in the second part. This is correct?
Yes. So we do not have a good understanding on the channel case yet in the multi-pairing case.
Okay. This is slightly confusing. So, and second, so you consider, this is one comment, you consider FC, feature information. So essentially, you are considering FC, okay?
Right.
Can you hear me? You are,
Yes.
second part, you consider FC.
Yes.
But somehow you did not explain the relationship between FC and covariance matrix. But this is essentially same. So inverse of FC equal to the covariance matrix by using the suitable data processing. So it is better emphasize that part. So otherwise, these two discussion, the relationship between that two kind of discussion is very unclear. Can you understand?
Yes.
Inverse of FC equal to the covariance. Covariance matrix.
Right. So this first inequality is achieved, is settlable when mu is sufficiently large. So this, yes, covariance matrix inverse is kind of mu times FC.
Yeah.
Any other questions, comments? Also from people online? So maybe I have one small question. So you mentioned that the quantum, you can implement the quantum switch with a quantum circuit. I thought that was not possible. Can you comment on that?
Not possible to realize it, or not possible to improving the quantum efficient machine.
Possible to realize switch with the circuit.
The quantum switch can be realized. So actually, that's already like kind of a experiment on this in this paper. They already demonstrate
Closed time curve. That's written in the first paper by people in Pavia, where they prove that if you realize a quantum switch with a quantum circuit, you have a closed time-like curve. And so that's not a circuit. Have you read it?
Okay. So I'm not aware of that paper, but
About the quantum.
So in the circuit probably depends on in which sense. So this kind of a super quantum map, super quantum channels. So I don't know see like if there's any problem in their physical realizations in this paper, but maybe I have to look into the paper you mentioned, see whether there's
there are physical realization. Okay, thank you. Any other questions, comments? Okay, online, let me check once more. No, okay, if everything is all right, I would thank the speaker again.
All right, thank you.
Thank you very much. And I would move to the next talk, which is happening here physically by Dr. Arai. Yeah, we are a little bit ahead of schedule. What do we do, Masahito? Do we wait until 3:20?
Yes, maybe it is better to wait.
Okay, so we will resume in 5 minutes.
新井くん、いますか？
今ちょっと。
これ所属間違ってんだけど、一応1000円で入れないと、一応いけないことになってるんで、チャイニーズユニバーシティ香港の後。まあいいや。
Okay, so I think we can start. The next speaker is Hayato Arai, who will tell us about a work in collaboration with Masahito Hayashi on the derivation of quantum theory.
Can you hear me? Okay. Thank you for the introduction and thank you for inviting my talk. So I talk about my recent work, the derivation of standard quantum theory via state discrimination. This is a joint work with Masahito Hayashi. And if you want to know the detail of this talk, please see this archive paper. So first, I will give an abstract of my work. So our work addresses on the foundation of quantum theory or foundation of quantum information science. So we aim to derive the model of quantum theory by applying the state discrimination in general paradox theories. And mathematically, our work is based on the matrix analysis. And as a result, we obtain three main results. Okay, this is the outline of my talk. So first, we introduce the concept of general paradox theories. So first we explain the motivation of the general product theories out. I do not on the video. Okay. Yeah, the model of mathematical model of quantum theory is well successful to describe the physics. However, there are many open things of the foundation of the model of quantum theory. So, and there are several studies. So the general product theory here after GPTs. GPT is not a large language model, not related to large language model. So anyway, so it's a modern approach to characterize the model of quantum theory, focus on the probabilistic structure obtained by the state and measurement. The aim of GPT is single quantum theory out as other general models by using operational postulate or physically meaningful postulate like this figure. And so sometimes, so this is a problem. What is a meaningful? So in this work, especially we focus on the performance for an information task as a postulate. So it is important because it can be regarded as an implicit limitation of physical experiments. So, and also, this work aims to single quantum theory out of the subclass of general models called quantum-like models. So this is our motivation. So, and here we explain the mathematical background for some mathematicians. There are not so many mathematicians here, but so anyway, so after that, we define a model of general probability theories. So, and this is based on the positive cone. So positive cone is a subset of a finite dimensional linear vector space within a product, satisfying these three properties. And for a positive cone, we define a dual cone as that this is all element such that the positive for any element in the original cone. So simply speaking, a positive cone is such a cone whose vertex is 0 on the vector space, and the dual cone in such case, and the ray is orthogonal. And a typical example of positive cone is a set of positive semi-defined matrices. So in this talk, we denote this as a set of Hermitian matrices, and this is as a set of positive semi-defined matrices on the finite dimensional Hilbert space H. So and the dual cone of this is equal to itself. So there are many examples of positive cone. So we in this study we consider only the case of V equal to the set of Hermitian matrices with a Frobenius in the product defined by the trace. Okay, next we define a model, quantum-like model. So we start the model of quantum theory, and this is also a remark for the mathematician. So in this talk, we say that when we say that define a model, then we define the three things: state, measurement, and the probability obtained from states and measurement. The states is an element, and measurement is a family. When a state is measured by some measurement, then we obtain outcome correspond to the index with some probability. So quantum theory is such a model. A state is defined as a density matrix, and measurement is defined as a P of n, and the probability is given by the trace. So the important thing of this definition is that they satisfy these requirements. First, the state space and measurement space, this means a set of all states and set of all measurements, are convex. And second and third is condition for this value is exactly composed of the probability distribution. So anyway, so in this sense, the important thing, also important thing is that so the quantum theory is determined by the set of positive semi matrices. So the quantum-like model, the definition of quantum-like model is a generalization to replace the set of position feminine matrices as a general positive cone C like this. So the important thing is that in such a generalization, even in such a generalization, the requirement is also consistent. So this is a definition of quantum-like model. So because we consider the general positive cone, so we can available non-positive state and non-positive operator value measure can be available in quantum-like models. So this is a setting. And here we remark that why do we consider quantum-like models? So actually, a model of GPT can be defined in more general object vector space and in a product and positive cone. But this work needs to compare the performance of state discrimination between general models and quantum theories. And the performance in quantum theory is given by the trace norm. And then in order to deal with trace norm, we need to consider a vector space composed of matrices, especially Hermitian matrices. But, so this is a good thing. So if the dimension of the vector space is square, so any general model, in this case, any general model can be modified to a quantum-like model. So then our restriction is essentially related to only the dimension. But anyway, this is an open problem. What is the physical meaning of the condition of the dimensional condition? But anyway, so we consider quantum-like models defined as follows, defined as this. And there are continuously many models for each positive cones. And we aim to derive the quantum theory out of the many quantum-like models by applying the performance for state discrimination. So this is a motivation and setting. So then we explain the state discrimination. So what is a state discrimination? State discrimination is an information task that, so first we are given an unknown state rho, and its candidate rho 0 and rho 1, like this, and apply one-shot measurement M. So one-shot measurement, and we obtain its outcome I. But then, by using information of outcome, we aim to identify the unknown state with high probability. This is the task of state discrimination. In standard setting, we determine rho is equal to rho I if we obtain the index, the outcome I. So then, in this case, there are two types of error. So first, we determine rho equal rho 0, but the actual state is rho 1. The corresponding probability is given as this one. And second type of error is that, so we determine rho equal rho 1, but the actual state is rho 0. Corresponding probability given as this. And we focus on the sum of two types of errors defined as this. So this corresponds to the actual error probability when the candidate state rho I is given with the same probability 1 over 2. And also, so if the sum of errors is equal to 0, then the total error probability is 0. So especially in such case called perfect discrimination case. So in the preceding study of standard quantum information theory, the error sum is well studied. So first, so we introduce the two results. So first, so the equivalent condition for the perfect discrimination is given by the orthogonality of candidate states. And second, the error sum is bounded as so error probability is bounded as follows, given by the trace norm. So in this talk, we call this inequality a quantum bound. So error probability is error probability is always larger than this value. This is called quantum bound. And also we studied so in some class of quantum-like models, and we obtained the result that so both conditions, the candidates are non-orthogonal and perfect discrimination can be compatible in certain quantum-like models. So this means that this means the violate, this violates the equivalent condition. Moreover, this violates the quantum bound because the non-orthogonal states can always satisfy that the trace is strictly less than 2. And therefore, they satisfy the opposite inequality. So this case violates quantum bound. But our present study, we do not analyze general situation, general model of general quantum-like models. So we have a question: so when such a violation of quantum bound appear in general quantum-like models? Yes. So we start with this question, and finally we derive the quantum theory via the quantum bound. Okay, next we explain the main results. So firstly, we explain the main result 1, general bound of set definition. As a preliminary, we define the value Rm for 2 outcome measurement M, defined as the range between the maximal eigenvalue and minimum eigenvalue of one of the matrices Mi. So this definition is independent with the choice of the index I, because the matrices satisfies the summation condition. Sorry, this summation condition, this one, and this equality implies the equations between the maximal eigenvalue and minimum eigenvalue of M1, M0 and M1. And this relations implies the range is independent with the index I. And by considering the range M, range Rm, so we obtain the lower bound of error, the error sum. So consider any quantum-like model defined by C. So any pair of 2 states and any measurement in a model, they satisfy this bound. So this is quite similar to the quantum bound. The difference is only this part. And actually, in quantum theory, the range is always less than 1. And therefore, this theorem reproduce the quantum bound, this one, simply. And in other words, the range, if the range is strictly larger than 1, such a model might violate the quantum bound. So in other words, this condition is necessity for the violation of quantum bound. And we actually can show the sufficiency. So we obtain equivalent condition for violation of quantum bound as follows. So consider any quantum-like model defined by C and give a measurement in the model. Then the following 2 conditions are equivalent. So there exist 2 states in a model. They satisfy, they violate quantum bound. In other words, they satisfy this inequality. And second, the range is strictly larger than 1. So, but here we remark that, so any measurement that is not quantum measurement, that is not P of M, is not necessarily satisfy this condition, because there exist non-positive operator valid measure satisfying the range is not larger than 1. So the proof of the theorem 2 is shown as follows. So also the implication 1 to 2 is shown by the theorem 1, as I mentioned just before. And the implication 2 to 1 is shown by the exact construction, construction of states satisfying this inequality. And then so theorem 2 states that if there exists a measurement satisfying this condition in the model, then the model violates quantum bound. So by using this logic, we derive the quantum theory under the condition. So we obtain the theorem 3. You consider any quantum-like model defined by C, and under the condition that the measurement space of the model is larger than the measurement space of the quantum theory, then the following conditions are equivalent. First, the cone is equal to the positive semi-finite matrices. In other words, the model is quantum theory. And second, any two states and any measurement in the model satisfy quantum bound. So the proof of implication 1 to 2 is just a quantum bound. So this is shown as a present studying standard quantum information theory. And the implication 2 to 1 is shown by construction, a measurement satisfying this this condition under the original condition of this one. And this one can be written as this opposite inclusion relation of the cone. So the theorem 3 states that under the condition of this original condition, so the quantum theory is the worst model in terms of error sum of state discrimination. And this condition can be written that so all P of M's are available measurement in the model. So in such under such condition, quantum theory is the worst model. Okay, we summarize my result. So the sum of error can be well solved even in quantum-like models. So we obtain a new general bound of error sum, and we obtain equivalent condition for violation of quantum bound of error sum. And by using this, so quantum theory is characterized by quantum bound for state discrimination under the condition that all P of M's are available measurement in a model. So this is quite new approach to derive quantum theory through performance for information tasks. So this is a very novel approach to derive quantum theory, the model of quantum theory. Finally, we give open problems. So first, the relaxation of the additional condition of theorem 3. So we cannot find any counter example if we relax the additional condition. And second, the generalization to the hypothesis testing setting and initial asymptotic setting. So in this case, we consider instead of the sum of errors, we need deal with each types of errors, this one, separately. So can we deal with such a separate calculation? This is the open problem. And also, what is the general asymptotical rate in general quantum-like models? This is open. And third, so the extension to the any general model without the condition, dimensional condition. So in this work, this condition is necessary to deal with a trace norm. Therefore, in order to deal with general model without this condition, so we need to more general measure of the performance for state discrimination instead of the error sum. So that is all of talk. That is all. Thank you for listening. Thank you for that.
Thank you very much for the talk. So as usual, I start here from the people that are in front of me. If there are questions, comments.
Question from mathematician is also welcome.
So let's see online. If not, I have a question. Anybody online? So maybe I can start.
Baichu, do you have any question or comment?
Not yet.
Not yet. Yeah, okay.
I have one.
Okay.
May I? Okay, so when you say that quantum theory is the worst in discrimination,
yes,
I don't understand very much the logic there. So I would say that quantum theory maybe is the one for which discrimination is exactly captured by trace distance.
Yes.
And I would say that it is very natural to say that if the cone of states is different from the one in quantum theory, or better said, that if the set of measurements is not the cone of positive operators like it happens in quantum theory, then the trace norm is not the right distance to consider.
Mhm.
Maybe one should optimize instead of, I mean, the trace distance is implicitly optimized over all positive semi-definite operators.
Mhm.
So instead, if one defines an alternative trace distance optimizing over all generalized measurements, then still the bound should hold, because
Yeah,
the
yeah,
bound is really just linear algebra, right?
yeah.
Okay.
Yeah. But so the worst case, it means any quantum-like model we define today. So when we consider more general measure with explanation, we can consider more general models, not composed of the Hermitian matrices, more general case. And when we consider the only model composed of Hermitian matrices, then the model always violates the quantum bound under the condition of the measurement availability.
Okay, thank you. Any other comments? Also from people online?
May I ask a question?
Yes.
So, if I understand it correctly, the result of your theorem 3 is very strong. So you have excluded all the non-quantum GPT theory if you using the condition 2, right?
Yes. If this condition and under the condition, so using condition 2 means
Assuming the cone.
a cone.
I mean,
Oh, okay.
Yes.
Oh, thank you.
Yeah. We exclude any other general quantum-like models.
yeah, quantum. Yeah, that's important, right? It's not that any other GPT is
Yes.
excluded by this. Yeah.
Yes.
There's quantum-like models
Yes.
only.
Yes.
Okay.
Okay. So I think that we can thank the speaker again. There are no questions here online. Let me check once more.
Maybe no one.
I see nothing on the chat. Okay, so let's thank the speaker again. Still have 5 minutes and we will wait for 5 minutes longer. Okay, so it's 3:50 in Japan, 2:50 in China. So I think we can start the next talk by Bai-Chu Yu about measurement device independent detection of beyond quantum states. Please.
Okay, thanks a lot for introducing. Hi, everyone. Today I'm going to give a talk about the topic of measurement device independent detection of beyond quantum states. And the talk will be divided in, it's mostly about 3 parts. The first part is the introduction of non-detectability of beyond quantum positive over all pure tensors. We'll call it POPT states in standard Bell scenario that is device independent. The second point is that the generalized Bell scenario with quantum input, the introduction of this one, which is measurement device independent. The third point is the detection of beyond quantum POPT states with MDI Bell tests. Okay, so let's go into this. The first is I will have a brief introduction to the standard Bell scenario. The standard Bell scenario is a very simple scenario that consists of 2 spatially separated parties. We call them Alice and Bob, and each of them is gets input, classical input, X and Y, and they are asked to output some classical label A and B. So in such scenario, the whole experimental setup of Alice and Bob are treated as a black box. That is, we do not need to know any information about how they process the input and generate the output. So all we know is just statistics. Here, the PAB given XY, the set of statistics generated by this scenario. So we also call this such statistics correlations. So such scenario has the characteristic of has the property of device independent. So that means that because we do not need to know the device. Because of the device independent property of Bell scenario, so it is a very convenient tool for studying theories other than quantum mechanics. So the purpose of studying other theory has already been mentioned by Hayato just now, because there are many fundamental problems that has not been well addressed by now. So generally, as far as I know, the main method of studying such theories there are two ways. The first, they rely on some physical principles. For example, they propose some physical principle and set up some constraints and find the theory that does not violate such constraint. But usually such method only provides a boundary for the correlation, but not the exact description of the theory. The second way is that based on the experimental statistics we obtained, and find out what kind of mathematical framework can be compatible with such experimental statistics. And also, just now, I think what the Hayato's work, he combined the two types. He considered a practical task which contains some physical principles, and also he used the constraints of some mathematical framework. Okay. And next, we briefly introduce the general probability theory, that is GPT. So I will introduce in another perspective. So GPT is a general framework to assign probability for each outcomes in an experiment. So it just contains two weak assumptions according to the reference I found. So the first is that each choice of preparation is made independently from each choice of measurement. The second is that repeated runs of the same measurements yield an independent and identically distributed source of data. So of course, there are many different description of the GPT, but I think the one I found in this reference is very simple to me. So as an example, we can consider a two outcome case. Then where the PI, the set of PI are defined as the M different preparations. Later we'll see it can be described by states. And the set of MI, there are and maybe here should be MJ. There are N measurements. So the general probability theory, GPT, can be described by a matrix, which is the probability of getting result 0 given each preparations and even each measurements. When the outcomes are more than 2, then we just need to add more outcome in this matrix. Okay. So let's come to the states and effects of GPT. So first, we will see that if we remember the matrix D just now, if the rank of this matrix is K, then we can find a set of K-dimensional state vectors and a set of also K-dimensional effect vectors, EJ, such that each element of this matrix can be written as the inner product of SI and EJ. And also, the second result is I found in the Hayato's paper just now, and this result is I made a slight modification. So it's if K is equal to the square of D, then we can find set of matrices SI and in the space LHD. So LHD here is the space of Hermitian matrices on Hilbert space of D-dimensional. So then, and the set of matrices EJ also in LHD, such that each Dij equals the trace of their product. So the result 2 give us a way to associate a special kind of GPT to the Born rule. And in the following contents, we talk about, we will adopt such assumption, where we assume that we actually know the dimension, or more exactly, local dimensions of the system. So let's come to the introduction of POPT states. So to briefly speaking, POPT states are Hermitian unit trace operators, which they can produce non-negative probabilities under local measurement operators. So because of the Bell scenario, in Bell scenario, the measurements are restricted to be local. So we see, although POPT states can have negative eigenvalue, but it does not produce negative probabilities in Bell scenario. So in the following, we will call the POPT states with negative eigenvalues beyond quantum states. So we will see that the inclusion relation between the POPT state and quantum states, because the dual cone, which is the measurement, is separable. The measurement, the set of measurement becomes becomes smaller. So the dual space of the states, dual cone of the space becomes larger. Okay. Then I'll clarify the goal of this work. So the goal is to distinguishing the beyond quantum POPT states. So usually we do not consider the existence of POPT states because they have negative eigenvalue. But I think they are still possible to exist because the knowledge of measurement operators in the experiment is a strong assumption. So we could not exclude the possibility that the measurement operators we use are not actually those we think. For example, because an entanglement measurement is very complicated to perform right now. So in the process, we cannot guarantee that in the process of an entangled measurement, there is not a quantum channel that also included, which changes the tested states or equivalently changes the form of the measurement operators. So our goal is distinguishing beyond quantum POPT without the need of the knowledge, or we say trust, to measurement operators and moreover the knowledge of the tested states. So the first protocol we can consider, we can think of course, is the DI protocol because it does not need any information of the both. But however, we have a result that the standard Bell scenario cannot detect beyond quantum POPT states. It is described like this. When the number of the subsystem is 2, for any non-quantum state, we can always find a positive and trace-preserving local map F on subsystem B or A, such that the beyond quantum state, is beyond quantum state, can be obtained by forming this map on a proper quantum state. Then the following in the equation in the green box shows that why we cannot detect them, because the map on the quantum states can be changed equivalently into a dual map on the measurement operator, which just changed the local measurement operator B, MBB, into another one. So the whole set of correlation is still inside the quantum correlation, the boundary of quantum correlation. Okay. So it seems that we have to compromise to add some additional trust into the protocol to detect to distinguish such states. So the protocol I consider is that it's called the general Bell scenario with quantum inputs, which are originally proposed by reference 3. So we see it's very similar to the quantum Bell scenario. The only difference is that the input, which is originally classical, is changed into trusted quantum states, tau x and tau y. So by introducing the additional trust on the quantum input states, so the measurement device independent Bell scenario can certify certain properties of the measurement operators, which is different from the DI scenario. And also it can close some loopholes, such as locality loophole and detection loophole in the standard DI Bell scenarios. So the reason it's called measurement device independent is that we can see that the system of Alice and Bob is still treated as black box. The assumption that we add into is on the auxiliary state, that is the quantum input. Okay, so let's come to the results. First, we see the equation of the correlation generated in the MDI detection can be written as the first equation here. So we see that the rho AB is some general POPT state, and the measurement MA prime small a is just the joint measurement operator on either side, where A prime means the auxiliary system, which contain the input state. Okay, then we see the correlation can be equivalently generated by an operator pi AB, where this is the representation of pi AB. And we have two propositions, the following. The first is that if rho AB is a quantum state, this operator pi AB would be a positive semi-definite matrix for any pair of output A and B. So this is very straightforward. And we have also the second one. So when the measurement operators are entangled, so pi AB may preserve the negativity of PAB, rho AB, especially so when the dimension of system A and A prime, B and B prime are equal. So, and the measurement operators are taken as generalized Bell measurement operators. So we see that the pi AB is just performing some local unitaries on rho AB transpose and times some coefficients. So we see that the central problem is of the detection now is that first, we must find suitable measurements such that pi AB can preserve the negativity of the tested beyond quantum state. The second problem is that we should find efficient method to recover the information of pi AB from the experimental correlations. Then for problem 1, we get the following result. First is that pi AB preserves the negativity of a beyond quantum state only if the two measurement operators are entangled. This is quite straightforward. And the second result is that in the 2x2 dimensional case, pi AB preserves the negativity of beyond quantum state if first, the state is also an extremal POPT state. And second, the measurement operators are entangled pure. And the key of the proof is the point that any 2x2 beyond quantum state rho AB can be obtained by performing partial transposition on some suitable entangled quantum state. So when the beyond quantum POPT state is also extremal, the corresponding entangled quantum state is pure, then the following proof is very straightforward. But from the result, we also see that when the measurement operator is not general Bell measurement, the detection power becomes much less. We can show the counter examples if any condition of the two is not met. So if we can, we should keep our measurement operators to be general Bell measurements for the detection. Okay. To address the second problem, we use a semi-definite program that is inspired by the reference 4. To understand this SDP program, semi-definite program, it is just reconstructing the least negative matrix XAB, which is minimize the absolute value of its smallest eigenvalue, which produce correlations compatible with pi AB. So when there exists, when we can find any CAB that is larger than 0, then we can confirm that the state is beyond quantum. Then we also assess the performance of our scheme. We propose 2 criteria of the performance. The first is universal completeness. That is, any beyond quantum state can be detected by the protocol when the experimental devices are well chosen. The second criterion is soundness. Quantum state will never be detected as a non-quantum state by the protocol. Then we have the following 2 results. The first result, I won't read the result, I just say what it means. So the first result says that the protocol guarantees soundness with a trust on the input states, which is just the basic requirement of MPI protocol. The second result, result 4, shows that the protocol satisfies universal completeness with the knowledge of the local dimension of the tested system. So such a result improved the result of the former reference. In this reference, the authors also considered detection beyond quantum state with measurement device independent protocol. However, their protocol need the complete tomographically complete information of the tested states. So, but we just need to know the local dimensions of the tested system. And also, we consider in the next we consider the performance when the input state is not tomographically complete. We obtain that when the local dimension are 2, and if any input sets consists of no more than 3 linear independent states, that is one state less than the tomographically complete case, then, and if the measurement operators are Bell measurement operators, we can always find some beyond quantum state that cannot be detected with one pair of outcomes. So this theorem means that when we use the general Bell measurement operators in the detection, so using tomographically incomplete set of input states does not necessarily reduce the complexity of the experiment, because we need to consider the correlations of multiple pairs of outcomes instead of just one pair. Okay, and also another result is that when the local dimension is 2, if we can find a state such that the state are orthogonal to any of the input states tau x on Alice side, so no beyond quantum state can be detected by the protocol. This is also similar for the Bob side. This shows that in order to detect at least some beyond quantum states, when the local dimension is 2, we need at least 3 quantum input states, each for Alice and Bob. And additionally, these input states should be linear independent and non-orthogonal. Okay, and now is the summary. So we propose measurement device independent Bell test protocol, which can distinguish beyond quantum states. And we show that our protocol just need to assume the local dimension of the tested system to achieve universal completeness. And there are some points to be done. The first important point is that we should take into account of the experimental errors, because there are previous work which states that when the experimental errors of the noisy environment is considered, even if the state is quantum, sometimes the operators pi AB we reconstruct can be negative. So we need to consider such case. The second is that we should make the result of tomographically incomplete case stronger, because now it seems it has too much restrictions. Okay, that's all for my talk. Thank you.
Thank you very much for the presentation. Any questions, comments? Yeah.
I'm Hayatari from Nagoya University. Thank you for interesting talk. So my question is very simple. So how about the multipartite case? So maybe standard Bell scenario, in the standard Bell scenario, so some of beyond quantum states can be detectable, but not all beyond quantum states can be detectable in multipartite scenario of the standard Bell scenario. How about the generalized Bell scenario?
So you mean the multipartite case? How do we detect beyond quantum POPD state, right?
Yes.
Oh, so I think for the DI protocol cannot distinguish POPD state only in the case where the subsystem is 2. For multipartite case, even the DI protocol, in the DI protocol, the POPD state with the correlation of that POPD state generate is larger than the quantum correlation. So it's much simpler.
And so how about the generalized Bell scenario case? In the
generalized what?
You are generalized Bell scenario case. So from with a quantum input case.
Oh, okay. Then let me see. I think it's still workable, but it's not very easy to describe it here. But
Thank you so much.
yes, I think it's still doable.
Yeah.
I think you can do it. Yes.
Yeah. Thank you. Yes.
So I'm confused. So general bell means bipartite case. I cannot understand what is the meaning of generalized bell state.
Oh, so general bell, because the definition of bell states is usually in the two-dimensional case. The generalized bell operator is the also bipartite case, but there are higher dimensional
Only higher dimension case.
only higher dimensional case. Yes.
Any other question? I have a little question actually. So at some point you show a slide when you say that if you have a POPT state, then there always exists a positive trace-preserving linear map acting locally that brings you back to the set of bipartite quantum states, right?
Yes. This is the
This slide exactly. So it could be actually you can even specialize it to the completely positive trace-preserving local map, right? You need only positivity, sure, but
I think it is just positive here because completely positive.
oh, right. So sigma is the quantum state, and you can transform it into a POPT state. Okay. Did you show this, or is it in some?
It's already known result. Yeah.
Okay. Which is the which reference is that?
Oh, there are two references. One is the. Oh, I'm sorry, I did not take down the reference, but also one of our former in one of our former paper with Hayato, we also proved this result. I can if you want I can send you personally later when after I found the reference.
Okay, thank you. Any other comments? No, if not, so let's thank the speaker again.
Thank you.
So we have still 2 minutes. Oh.
(30 秒. ああ、次ね。5時までです。
Okay, so the next talk, and it's also the last talk of this session, right? Let me check. Yes, is by Ryuhei Mori from Nagoya University in collaboration with Ryo Ito about lower bounds on error probability of quantum channel discrimination by the Bure's angle and the trace distance.
Yes, thank you for the introduction. I'm Ryuhei Mori from Nagoya University, and this is joint work with Ryo Ito. He is a student at Tokyo Institute of Technology. And by the way, I already uploaded my slide to the website. Please check the abstract section on the right side of the title of the talk. I uploaded some slides of the talk. Okay. And the problem is very fundamental problem. It is called quantum channel discrimination problem. First, we are given the fixed finite set of quantum channels, phi1 to phi k. These channels have the same input system and output system. And then we also given the probability distribution on the quantum channels. And input of the problem is oracle. This oracle O is unknown, but oracle is chosen from the finite set of quantum channels. So oracle is either of one of phi1 to phi k. And these are chosen according to the probability distribution P. Okay, some question? Not question, okay. And our goal is to determine which quantum channel is given as oracle. So this is very fundamental problem in quantum information science. And general algorithm for this problem is like this form. Here, we fix the number of queries to oracle. It's fixed to be n, and oracle is chosen from this set, phi1 to phi k. But once oracle is fixed, oracle is always the chosen same quantum channels. And then here, gamma 1 to gamma n are general quantum channels we can design, and m is also general measurement we can design. So first, we prepare ket 0 and apply general quantum circuit gamma 1, and then we call oracle O, and then we apply general quantum channel gamma 2, and then we call oracle O, and so on. And then we call oracle n times, then we measure the quantum state, and then we output the index of the chosen quantum channel. Index is 1 to k. This is a general algorithm for quantum channel discrimination problem. So our goal is to obtain lower bound of the this problem, lower bound of the error probability of this problem. So here, if we fix gamma 1 to gamma n, of course, we can optimize gamma 1 to gamma n, but if we fix gamma 1 to gamma n and we only consider optimization of m, the problem is equivalent to quantum state discrimination problem, because if, for example, if oracle is equal to phi1 and gamma 1 to gamma n is already fixed, then the quantum state just before measurement is fixed to some quantum state, rho 1. And if oracles are phi2, the quantum state here just before measurement is fixed to some quantum state rho 2. So problem is equivalent to quantum state discrimination problem. Quantum state discrimination problem is defined in this way. Quantum state finite set of quantum state is given, and probability distribution on the quantum state is given. And then quantum state law is chosen from the finite set with this probability distribution, and then determine output index of the chosen quantum state. This is a quantum state discrimination problem. And in this case, especially if number of quantum states is 2, the largest success probability of discrimination is known. this is expressed by using trace norm. Yeah, this is called Horebo-Hellstrom theorem. I think this theorem already appeared in first talk of this afternoon and second talk of this afternoon. Yeah. Okay. And this trace distance can be evaluated by semi-definite programming. And for more than 2 quantum states, the similarly largest success probability is a solution of some SDP. So in the case of quantum state discrimination, the largest success probability can be computed by solving SDP. So the problem is, but our problem is quantum channel discrimination problem. Next, consider the simplest case. Quantum channel discrimination of 2 quantum channels with a single query. So n number of queries is fixed to 1. In this case, the probability of success, largest probability of success is given in this form. Here, this norm is called diamond norm, defined in this way. The definition of this is very meaningful, easy to understand. This low AR is quantum state. This corresponds to quantum state here. Quantum state here, just after gamma 1. This is a general quantum state, low AR. Then OAR, then apply oracle O. Then we measure this state. We distinguish this state. So we input low AR to gamma. This gamma is in fact phi1. For example, phi1 is here. Then this is one of the state in the quantum state discrimination. And if this gamma is phi2, this is another state in the quantum state discrimination problem. So if low AR is fixed, the largest probability of success is given in this way. And finally, we take maximum for input state. So this is the meaning of this equation. Yeah, and this is called a diamond norm in the context of quantum information science. Maybe mathematician called completely bounded trace norm for this quantity. And then similarly, if we consider the restricted algorithm, non-adaptive algorithm that is parallel, also it is called parallel algorithm. In this algorithm, all queries are called at once. So n queries are called at once. In this case, similarly, the largest probability of success is given in this form. But here, the size of SDP is exponential with respect to n, so it's not easy to compute this quantity for large n. And in this work, we consider general adaptive algorithm with n queries. These are known result for simple cases. And then, so here I introduce some previous qualitative result. First result is there are 2 quantum channels that cannot be distinguished exactly by any non-adaptive algorithm, but can be distinguished exactly by an adaptive algorithm with 2 queries. So this example shows that there is 2 quantum channels that cannot be distinguished exactly by any non-adaptive algorithm. So if number of queries increases, error probability decays, goes to 0, but cannot be exactly equal to 0. But there exists adaptive algorithm that's with only 2 queries with error probability exactly equal to 0. So this means that adaptive algorithm is powerful than non-adaptive algorithm. And second result say for any 2 quantum channels, either of the following is true. Quantum channels can be distinguished exactly by finite queries, like the above example. And second case, the error probability of quantum channel discrimination decays exponentially in the number of queries. So there is no cases that error probability decays polynomially or doubly exponentially, or always exponentially, or exactly zero is finite query. Okay. So our result is more quantitative result. This is a table of our work and previous work. For number of channels is equal to 2, the simplest case is quantum unitary discrimination problem. This is the special case of quantum channel discrimination problem, in which the quantum channels are always unitary channels. In this case, Kawachi, Kawano, Lucara, and Tamaki showed minimum error probability of this problem in a simple way. Yeah, and then for more general quantum channel discrimination problem, Pirandra et al. Use technique based on port-based teleportation, and they show some numerical result. And we also derive new lower bound of error probability on this setting. And for some example, our lower bound is larger than their lower bound. Not always better, but in some cases, our lower bound is better than their lower bound. And for number of channels greater than 2, Zarka showed that Grover's search is optimal when number of marked element is equal to 1. So in the Grover's search setting, there are M element and there are L marked element, and Grover's search try to find one of the marked element. And if L is equal to 1, this problem can be regarded as quantum unitary discrimination problem, because there are M element and each unitary matrix corresponds to each element, one of the element that corresponds to marked element. So this is quantum unitary discrimination problem. And Zarka showed that if number of queries n is fixed, then Grover's search algorithm maximizes the probability of success. This is exact optimalities, not order, including constant factor. Grover's search is optimal. And Zwan and Pirandra showed some lower bound of error probability for more general quantum channel discrimination problem. And in this work, we consider a more general problem called quantum channel group discrimination problem. This is generalization of quantum channel discrimination problem. And this problem considers group of channels and output group may intersect, but the problem should output one of the group, including the channel. And this quantum channel group discrimination problem includes a global search for general L. And we also derive lower bound. And also we prove that global search is optimal algorithm for general L. So this was in the footnote of Zarka's paper, he wrote that his technique can be generalized to general L, but in my knowledge, no one proved the optimality for general L. And our results first time showed the optimality of global search for general L. Right? Yes. And today we concentrate to this case, number of channels is 2, because this is more complicated and idea is same. So we concentrate to this case, number of channels is 2, and show the lower bound of the error probability of quantum channel discrimination problem. Okay. Now, let's consider these 2 quantum states. These 2 quantum states corresponds to the quantum states just before the measurement of the algorithm. So first, initial state 0 is prepared and some algorithm gamma 1 is applied, then oracle is called. Here oracle is phi 1, and then so on. And then finally oracle is called, NS oracle is called, and then we obtain this quantum state. And finally, this quantum state is measured and determine index of the quantum state is 1 or 2. And similarly, if oracle is phi 2, we obtain this quantum state. So Horeb-Hellstrom theorem says that the error probability of channel discrimination is represented in this way. Here we assume that the probability for choose on phi 1 and phi 2 are uniform for simplicity. So 1/2 is here and trace distance is here. And here trace distance satisfies two important properties. First one is triangular inequality. For any quantum states rho sigma tau, trace distance between rho and sigma is upper bounded by trace distance between rho and tau plus trace distance between tau and sigma. And monotonicity, this says that for any quantum states, rho sigma, and any quantum channel E, the trace distance between E of rho and E of sigma is at most trace distance of rho and sigma. These are important property of trace distance. So now we are going to the very well-known simple technique for upper bounding trace distance. So now we want to upper bound this trace distance. Then we obtain lower bound of error probability. So first, I'm going to explain the simple technique. Then I introduce new technique and improves the previous technique. So first, we consider this quantum state rho 0 and rho n. Rho 0 was equal to rho 1 here, and rho n is equal to rho 2 here. But we also introduce a new intermediate states, rho 1 to rho n minus 1. The meaning is in rho 1, the first oracle call is phi 2, and the rest of the oracle calls are phi 1. And in rho 2, first two oracle calls are phi 2, and the rest of the oracle calls are phi 1. And similarly, in rho I, first I oracle calls are phi 2, and the rest of the oracle calls are phi 1. Then from the triangular inequality, we obtain this upper bound. Then it is difficult to upper bound the trace distance of rho 0 and rho n, but it's easier to upper bound the trace distance between rho I and rho I plus 1. So this is why we introduced these intermediate states. Then now we are going to upper bound each term. So trace distance between rho I and rho I plus 1 is equal to this. This is the definition of rho I and rho I plus 1. And these two terms are very similar. Difference is I's oracle call is phi 2. I plus 1's oracle call is phi 1 in rho I, but I plus 1's oracle call is phi 2 in rho I plus 1. This is the only difference. And left side of I plus 1's oracle call are common, so we can remove these quantum channels. Then we obtain upper bound because from the monotonicity. Because in the monotonicity, if we ignore common quantum channel E, then the trace distance is non-decreasing. So here, there are common quantum channel here, so we remove the common quantum channel, and then we obtain upper bound. And here, difference is only the final quantum channel, and inside of the quantum channel are common, so we replace the quantum state with general quantum state, rho AR, and take maximum. And this is a definition of diamond knot. So we obtain the upper bound of trace distance between rho I and rho I plus 1. And this is independent of I, so if we upper bound this by trace distance, there are n terms, so we obtain n times the trace distance here. So finally, we obtain this lower bound. So if we consider the quantum channel discrimination of rho 1 and rho 2, and these are given with uniform probability, then we obtain this lower bound of error probability. So this is a very simple technique. So now we are going to improve this lower bound. So here, in this lower bound, there are three inequalities. First inequality is triangle inequality here. And next inequality is here from monotonicity of trace distance. And the third inequality is here, replacement of quantum channel with the general quantum channel. So now we look at the triangle inequality. Triangle inequality is not necessarily tight. This is the intuition. If we consider the state vector and Euclidean distance like this, state vector is normalized, norm is equal to 1. So Euclidean distance is not tight in general, because triangle inequality of Euclidean distance says that Euclidean distance between phi0 and phi1 and phi1 and phi2, the sum of the triangle Euclidean distance upper bound the trace Euclidean distance between phi0 and phi2. It's true, but equality doesn't hold because from this figure, right? So always triangular inequality is not tight. Another candidate of distance measure is angle. If we consider angle, and angle, if use angle as distance measure, triangular inequality is tight, because angle between phi0 and phi2 is the sum of angle between phi0 and phi1 and phi1 and phi2. So this is the intuition. So we introduce angle for general quantum state, general mixed state. First, fidelity is defined by this equation, and this fidelity is between 0 and 1. So we can consider, we can consider arc cosine of the fidelity. This is the angle between the quantum states. This is called Bure's angle. So fidelity is between 0 and 1, and Bure's angle is between 0 and pi over 2. And trace distance and Bure's angle are related by this inequality, the inequality. Okay, so of course we are originally interested in left-hand side, but we can upper bound left-hand side by using fidelity. Then, so, and fidelity and Bure angle are essentially equivalent. And importantly, Bure's angle satisfies the triangular inequality and monotonicity. So our goal is to evaluate Bure's angle between low 0 and low n. And first, we use a triangular inequality, and complete the same way we obtain the upper bound of the each term. I do not explain detail because details are completely same as that for trace distance. We only use monotonicity here. So completely same. And this quantity can be evaluated by SDP, so it's easy to evaluate. So finally, we obtain this lower bound of error probability. And this quantity tau can be evaluated by SDP. This is independent of n. So the size only depends on the input and output system dimension of channels. And this is an example, concrete example. If we consider discrimination of two amplitude damping channel, I do not explain the definition of amplitude damping channel. Probably this was explained in the first talk of this afternoon. With damping rate R1 and R2, the error probability, lower bound of error probability is obtained in this form. So here we do not have to solve SDP. The tau is expressed explicitly like this. Here, this is the arc cosine of kind of Bhattacharya parameter. Yeah, especially distribution is uniform, the lower bound is more simpler. Okay, so this is very simple analytic lower bound of the error probability of discrimination of two amplitude damping channels. Okay, okay, this is a first technique, and next I'm going to explain the second technique. This is completely different. This is different. In the second technique, we still use trace distance. We do not use Pugliese angle. We still use trace distance, but we introduce weight. So here, the triangle inequality is not tight in general, but if we introduce some weight here, R1, and we multiply R1, then triangle inequality may be tight. So similarly, here we introduce n intermediate states, and if introduce the weight appropriately, triangle inequality may be tight. But if we consider n individual parameters, it's difficult to optimize n parameters. So here, we assume that these weights are some geometric sequence. So intuitively, these weights are, first weight is 1, and weight is some smaller than 1, and weight is smaller. And at some point, weight is minimized, and then weight is increasing. So we assume that the sequence is geometric. So here, k is some integer between 0 and n, and alpha and beta are a ratio of geometric sequence, and weights are first 1, and then alpha, alpha square, alpha cube, and its geometric sequence, and alpha to k is equal to beta to n minus k, and then this weight is increasing, like geometric sequence. This is, yeah, our restriction for efficient calculation of our lower bound. So essentially, the parameter is alpha and k, and beta is automatically determined. Then we obtain this lower bound from this technique. Yeah, and this is a numerical result of our lower bound. Here, we consider discrimination of two amplitude damping channels with damping rate R0 and R0 plus 0.01. So phi 0 is amplitude damping channel with damping rate R0, and that phi 2 is amplitude damping channel with damping rate R0 plus 0.01. So that's why R0 is at most 0.99, because damping rate is at most 1. And then this brown cross corresponds to the lower bound obtained by Pirandra et al. This is very complicated lower bound and very specific for amplitude damping channel. And these are our lower bound. And previous lower bound is better for large R0, but for most of R0, our lower bound is better. This smooth curve corresponds to the lower bound obtained by Pugliese angle. This is analytic, so this is very smooth symmetric curve. But this curve is not necessarily good lower bound. And this green triangle corresponds to our lower bound using trace distance and weights. We optimize weights, but we optimize alpha, but we assume that k is n over 2. Intuitively, k equal to n over 2 is a good choice, but it's not true. If k is optimized, we obtain a larger lower bound like this. So yeah, this is a numerical result. So in this case, yeah, for many damping rate, our lower bound is better than previous result. Okay. So finally, I briefly explain our result for quantum channel group discrimination. Quantum channel group discrimination is a problem to find a group including a channel, and the group may intersect. Motivation is Grover's search. In the Grover search with L marked element, we consider n choose L, n not n, m, if we assume that m elements and we assume that L marked elements, there are m choose L channels. And we want Grover's search try to find one of the marked elements. So each element corresponds to the group. And so group intersect, of course, but it's sufficient to find one of the group. So this, our motivation is global search. And we obtain lower bound for this problem using Bureau's angle and trace distance with weight. And especially lower bound using Bureau's angle proves the optimality of global search. This was proven for the case with exactly 1 Mach delta by Zarka. This is the old result, but in my knowledge, no one showed this result for general L. Yeah, and our lower bound using trace distance with weight is numerically better than previously known lower bound for some cases. Okay, that's all. Thank you.
Okay, thank you very much. We have quite a lot of time left for discussion. So if there are questions, comments.
So I'm Shintaro Minagawa, and I would like to ask the setup, maybe in the slide 3. So I would like to know the role of the gamma 1, gamma 2, and gamma 8. So why this is this is they are necessary, because the evaluation of the error, then they disappeared. So I would like to know the reason why. Yeah.
So our problem setting is oracle O is given, and as oracle, and we can do anything. Restriction is only we can call oracle n times. That is a unique restriction. And so we can do anything. So we can apply any quantum circuit here.
Okay, I see. So I also would like to know the ket zero. So how many numbers of ket zero are needed?
It's a good question. It's unbounded. In fact, it's unbounded. Yeah.
I see.
But in this analysis, essentially, for example, here R corresponds to the auxiliary system, and here this dimension of R is, without loss of generality, we can assume that dimension of R is equal to the dimension of A here.
Okay.
Same for other place. Same. Yeah. For fidelity, it's true. We can similar quantity for fidelity here. Also, dimension of R is at most dimension of A. So yeah.
Okay, I understand. Thank you very much.
Sorry, I have a comment. Okay. Hello?
Yes.
So you consider channel discrimination, but with two channel with n application, but
Yes.
that kind of discrimination problem already discussed by community of information theory very actively. Do you know?
Maybe I don't know.
This is very serious because, for example, in the case of state discrimination, this one is extensively discussed, and this one is all that kind of discrimination error exponentially go to 0, and that exponent is already explicitly derived.
Children bound, yes.
Yes, channel bound, of course. And of course, in the parallel strategy, it is enough to optimize that kind of channel bound by changing that input state.
But
this
input
is the parallel case.
But input state may. This is still a difficult problem, I think. Because input state may enter.
In order to want to consider advantage of the parallel case, parallel case.
Sorry?
You did not consider that topic. Can you understand?
I couldn't hear.
There was a problem in the internet connection. Your voice stopped for. Can you repeat the last minute or something?
他の質問でも。
So while we wait for Masahito to come back online, are there any other questions, comments? Online, there was something in the chat, but maybe it was from before. Ah, no, okay, it was about my question. Okay, so what shall we do? Let's wait a few more minutes to see if...
Yes.
So,
Wait.
Okay, I'm Hayato Arai from Nagoya University. Can I ask a simple question? So, in the slide of numerical result, so in this graph, they are not included the diamond normal case. So how different is the diamond normal case and your new result?
I forgot. Yeah, I computed, but I don't remember. Yeah. Perhaps worse than
Yeah.
green triangle.
Yeah.
I think.
Now I can speak. So can I make a comment? Okay. So my comment is that, so why did you compare that kind of adaptive strategy and parallel strategy? In the case of parallel strategy, we can easily derive the optimum exponent by using the Chernoff bound.
No, I don't think so, because
Adaptive case. Parallel case. I'm considering parallel case.
Yes, but I don't think so, because we can input entangled state, so it's not.
So you can consider entangled input. So then you can two-state discrimination on entangled state.
But size of the state is large if n is large, so exponentially large size of system. Okay, so size.
So you want to consider that kind of correlated case, correlated entangled state.
Even if each system is cubic.
Correlated entangled state. Okay. But for example, you only consider quantum case, but there is so many results in the case of CQ channel case and classical case. In the classical case, there is no advantage by using the adaptive method for exponent. This is already known.
Really? I did. Thank you.
And also CQ channel case, also no advantage.
Okay.
This is known, both results shown by me. So, but only the QQ case, there is some difference. And in our paper, we already shown that there is some difference. There is some exact example. There is some difference between that kind of parallel case and adaptive case. There is some big difference for exponent. We discussed that special case. But おかしいな。なんか、 But anyway, so somehow quite strange. So there is so many existing results for that topic, and also that topic, that paper mainly discuss exponents.これでもなんで ID でよかったんだっけ? Hmm? あれ? 切れたの?
Okay, now there was a problem here. Okay, but I think that the discussion can be considered over. Is there anything you want to add, Masahito?
Hmm?
Do you want to add anything to the
Okay,
last?
so somehow so many troubles. So anyway, so okay, firstly we should close. So no. Today's seminar, today's workshop may be closed now. So tomorrow we will start same time. So we can make a free discussion from now. So we should stop now for this work.